Okay.
So we can start, and I'm happy to present the talk of Sergei Igonin about discrete Miura-type transformations.
Hello, everybody. Dima, thank you for the invitation to give this talk. As you can see on the screen, I will speak about discrete Miura-type transformations, gauge simplifications, and group actions associated with lag space for differential difference equations. The talk is based on 2 papers which are available in arXiv. Now, I would like to define the class of equations. We consider differential, we consider evolution differential difference equations of the following form. Here we have a vector function u of an integer variable n and a real or complex variable t. Ut is the derivative of u, and for an integer I, ui is also a function of n and t defined by this formula. So ui is a shift of the function u by of the following type. And according to this notation, so this happens for every I, for every integer I. In particular, for I equal to 0, we get u0 is just u. So this one equation is actually equivalent to an infinite sequence of equations, or an infinite sequence of ordinary differential equations of this type. For every n, for every integer n, we have this ordinary differential equation. Now we consider another differential equation of the same type with a vector function v and some integers a tilde, b tilde, which are not necessarily the same as the ones before. And now I define a Miura-type transformation from equation 2 to equation 1. It is determined, such a Miura-type transformation in this situation is determined by an expression of this form. So u is equal to f of some shifts of v. And the following property must be valid for every function v satisfying equation 2. For every such function v, this formula must, if we compute u by this formula, then the obtained function u must satisfy the initial equation 1. So we get, so a Miura-type transformation determines a map from solutions of equation 2 to solutions of equation 1. And this map should be written as an expression of this form with some fixed integers p and r. Now a classical example. Consider the Volterra equation, where u is a scalar function, and the modified Volterra equation, where v is a scalar function, and a Miura-type transformation is given by this formula, u is equal to v0 times v1. So if we take a solution v of the modified Volterra equation, substituted here, then the function u obtained by this formula will satisfy the Volterra equation, and this means that we get a Miura-type transformation from equation 5 to equation 4. Now, why such transformations are important? They have many applications, and I mention one of them. So I defined Miura transformations, Miura-type transformations for differential difference equations, but they can be defined similarly for nonlinear partial differential equations and for difference equations. And very often the following situation happens. When one tries to classify a certain class of integrable equations, one gets a big infinite collection of equations, but in the course of classification, very often one finds a few basic equations such that all other equations from the considered class can be obtained from the basic ones by means of Miura-type transformations. And, well, examples of this situation can be found in the following works. So the first one is about 1+1 dimensional PDEs. The second one is about differential difference equations. Here also differential difference equations, and here difference difference equations. Well, so again, one tries to classify some big class of integrable equations, and one finds a few basic equations such that all other equations are connected to basic ones by Miura-type transformations, and this allows one to manage the whole class. So we get an understandable picture. A few basic equations, and the other equations are connected to the basic ones by means of Miura-type transformations. Well, therefore, it is desirable to develop systematic methods for constructing Miura-type transformations, and I will describe one method in my talk. So, what are the main results? I will describe a method to construct Miura-type transformations for differential difference equations using gauge transformations and invariants of some Lie group actions on manifolds associated with Lax pairs of such equations. And the method consists of several steps, and one of the steps is the following. We will have a matrix Lax pair, and we will try to simplify the Lax pair by gauge transformations. And I will show some result in this direction. And this result about simplification of matrix Lax pairs is of independent interest, in my opinion. But here it will appear as one of the steps of the method to construct Miura-type transformations. The method, we have already considered several examples of some of which I will show, and I see that the method is applicable to a wide class of Lax pairs. The considered examples include Volterra, Itoh-Narita-Bogoyavlensky, Toda equations and their modified versions. Another example is a differential difference discretization of the Sawada-Kotera equation, which is a partial differential equation, and also Adler-Postnikov differential difference equations from this paper. Well, what we get here, the method works as follows. We take some known equation with the Lax pair. We try to simplify the Lax pair by gauge transformations. And if we are successful in this, then we apply some procedure to the simplified Lex pair, the procedure involving Lie group actions. And if that procedure is successful, we get new integrable nonlinear differential difference equations connected with the initial known equation by new Miura-type transformations. And so here I consider the differential difference situation, but but the last step about Lie group actions can be regarded as a generalization of a result of Drinfeld and Sokolov about Miura-type transformations for the partial differential KdV equation. In that paper from 85, they considered the partial differential KdV equation and its Lex pair, and they presented a construction of Miura-type transformations for this equation using the Lex pair and some Lie groups. Okay, now some terminology and notation. Here I repeat what kind of equations we consider. We have a vector function u of the variables n and t. N is an integer variable, t is a continuous variable. Ui is also a function of n and t given by this formula. And we introduce the so-called shift operator with respect to the integer variable n. It does the following. This shift operator replaces n by n plus 1 and ui by ui plus 1 in all considered functions. Now, what are Lex pairs for such equations? Matrix Lex pairs. We consider two matrix functions, m and capital U. Well, curly U. I think I will call it capital U. So both matrix functions depend on a finite number of the variables ui and a complex parameter lambda. Next, we suppose that the matrix function m is invertible. And the most important assumption is that the Lex equation holds. So equation 7 can be called the Lex equation. It must hold as a consequence of our initial differential difference equation. So this is the differential difference version of Lex pairs. Right. So if all those assumptions hold, then the pair mu is called the Lex pair for the equation 6. And what is the meaning of it?
In other words, M is a Darboux matrix for operator for the second Lex operator.
No. Well, okay.
That's exactly the definition.
You can say, well, if it is easier for you, maybe you mean I do not. Well, I am try to be careful and to be precise. So actually, there are many examples of matrix Lex pairs, and in my opinion, not all of them come from Darboux transformations.
No. I'm saying that equation 7 is exactly the definition of Darboux transformation for the second operator.
Possibly yes, but I'm trying to give a precise definition of a Lex pair, and in this talk I do not need a Darboux transformation, so well, it's not necessary to discuss them here. Okay, so now what is the meaning of equation 7? Let us consider the so-called auxiliary linear system we take a matrix function psi and also of the same variables n and t, and we consider the following system of two equations on psi. S of psi is m times psi, and dt of psi is capital U times psi. This is a system of two equations for one function psi. Therefore, we should check compatibility of this system of two equations on one function. And equation 7, if it holds as a consequence of the initial differential difference equation 6, this fact implies this fact is equivalent to the following fact: the auxiliary linear system 8 is compatible modulo the initial equation 6. So this is the meaning of equation 7. The Lex equation 7 expresses the compatibility condition of this auxiliary linear system. Now, if we have one Lex pair, we can produce many more by applying so-called gauge transformations. And a gauge transformation is an invertible matrix G, also depending on a finite number of the variables ui and parameter lambda. And here, and for any such matrix G, we consider m hat and u hat. And if m and u is determine a Lex pair, then m hat u hat is also a Lex pair. This is well known. And the Lex pair m hat u hat is said to be gauge equivalent to the initial Lex pair m u. Gauge equivalent with respect to the gauge transformation G. Now, so now the method to construct Miura-type transformations, it consists of 3 steps. On the next slide, I describe the first step, which is very simple. First, I introduce some notation. We have we have our vector function u, which is n component. Now u1, u capital N are scalar functions. We have the initial differential difference equation for the vector function u. Then subscript, you remember that we have we introduced ui with subscript I. Now I replace I by small l, so they are also vector functions, and they, using the shift operator, they can be written as follows. We apply the else power of the shift operator to the vector function u, and we have also the components of those vector functions. Now these quantities can be regarded as independent quantities, which are sometimes called dynamical variables. And in our matrix Lex pair, the matrices M and capital U can depend on any finite number of those variables and the parameter lambda. So in principle, we look now at the matrix M. It can depend on any finite number of these variables UL. And in principle, the small l can be can be any integer, including negative ones. So ul with negative l in principle can appear in M. But we want to get rid of ul with negative l, and this is very easy to do. because for any fixed integers L1, L capital N, we can make this relabeling. So this relabeling means that we make this this invertible change of variables in our differential difference equation, and using a suitable relabeling of this type, we can assume that our matrix M depends on UL with non-negative L. So in the matrix M, we see after such a after a suitable relabeling, we can assume that in the matrix M we get only U0, U1 up to UK for some non-negative integer k. So UL with negative L does not appear in M. We do not lose any generality in this step. Okay, now step 2, which is more interesting. We now consider a matrix Lex pair with M of this form, where M depends on U0, U1 up to UK and a complex parameter lambda. Now we recall that we can use gauge transformations, and we can apply arbitrary gauge transformations, and applying a gauge transformation to a given Lex pair, we get an equivalent Lex pair. Therefore, it makes sense to try to simplify our Lex pair by means of gauge transformations. And our goal is the following: we want to get rid of UI with all positive I in the matrix M. So we want to find a gauge transformation such that the corresponding matrix M hat depends only on U0. Right, so in the matrix M we have U0, U1 up to UK, and we want to find a gauge equivalent matrix which depends only on U0. And we do this step by step. First, we try to get rid of the variable UK. So first we try to find a gauge transformation which would allow us to get rid of the variable UK. And this can often be done as follows. We have here a theorem about this, theorem 1. Now, so our function depends on U0 up to U0, U1 up to UK, and suppose that the following condition 10 holds. Right, so just differentiation of M with respect to UK J, multiplying by M inverse, and then differentiate with respect to UI0. So suppose that this holds, then there is a gauge transformation G depending on U0, U1 up to UK minus 1 and lambda, such that the gauge equivalent matrix M hat is of this form. So here there is no UK. So in the initial matrix M we had UK, and after applying the gauge transformation we get rid of UK. All right, so how to construct such a gauge transformation for a given matrix M satisfying condition 10? There is an explicit formula as follows. We take a constant vector, substitute instead of, we substitute U0 equal to this constant vector A0 in our function M. And then do the following. So here is M with U0 replaced by A0. We take the inverse of it and apply the operator a to the power -1. Look what kind of variables do we get as a result. So here, after the substitution, the matrix M depends on U1 up to UK, and when we apply S to the inverse of S, we decrease the order of we decrease the indices for each U. Therefore, we indeed get dependence on U0, U1 up to UK -1. And it turns out that if our initial M satisfies condition 10, then this formula indeed gives a suitable gauge transformation, which allows us to get rid of the dependence on UK. Okay, so we get, in this way, we get rid of the dependence on UK. And what next? Then next step is we try to get rid of dependence on UK -1. So we check again the same condition with K replaced by K -1. If the condition holds, then we get rid of UK -1 and so on. If we are lucky, we get rid of L. So applying a finite number of gauge transformations, we get rid of UL for all positive L. And it turns out that this indeed happens in at least in some considered examples, and this construction is quite widely applicable. Okay, and here is one example. We take the differential difference equation called modified Bogoyavlensky equation, which is of this form. Here M depends on U0, U1, U2. And we want to get rid of U2 by applying a suitable gauge transformation. The above formula gives the following gauge transformation depending on U0 and U1. Applying this gauge transformation, we get this matrix, which depends on U0 and U1 only. So indeed, we get rid of U2. And it turns out that the same procedure can be applied to M hat to get rid of U1. This can be, well, the explicit formulas are presented in the first paper, which I mentioned. So indeed, here we applying two gauge transformations, we get rid of U2 and U1. And as a result, one gets a matrix depending only on U0 and lambda. And then one can use it for constructing Miura-type transformations by means of Lie group actions, which I will describe on the next slides. Okay, so step 3 of the method involving Lie group actions. So suppose that we were successful at the step 2, and after suitable gauge transformations, we have a matrix Lex pair such that M depends only on U and lambda. For such a matrix Lex pair, we define a sequence of groups H0, H1, H2, and so on. They consist of certain invertible d times d matrix functions, where d times d is the size of all matrices considered here. We define them by induction. The H0 is just the trivial group with containing only the identity matrix. Then H1 is generated by these matrix functions for all values of U and U tilde. And by induction, we suppose that HP has been defined, and we define HP plus 1 as follows. HP plus 1 is defined, is generated by the elements small HP from the group capital HP, and the following elements for all HP and all values of U. So an inductive definition of this increasing sequence of groups. Okay, now another very different group. This is a Lie group, and so it depends on integers d. It depends on d, c, k, where d is an integer, c is a complex constant, k is a positive integer. D and k are positive integers, and c is a complex constant. So it consists of invertible d times d matrices with entries from this quotient algebra. Equivalently, an element of this group can be described as a sum of this form. You see, it is a polynomial in lambda of degree k minus 1 with matrix coefficients, where the free term is an invertible matrix, and the other coefficients can be arbitrary matrices of size d times d. And we work, when we multiply two such polynomials, we work modulo the relation lambda minus c to the power k is 0. So we indeed work in the quotient, in this quotient algebra. Well, it is this group is a Lie group of dimension k times d squared. What are coordinates on it? Just the entries of the matrices w to the power k. The entries of these matrices can be regarded as coordinates on this Lie group. And we say that when we introduce short notation, capital G is this group depending on D, C, K. Okay. Well, it is important to remember the all the notation. This is why I put a lot of information on one slide in order to have as many objects as possible on one screen. Okay. Now, right. So again, our group capital G consists of such polynomials with matrix coefficients, and HP is consists of certain invertible d times d matrix functions of lambda. This allows us to define an action of HP on this group by left multiplication. So elements, we take an element of capital HP, which is a function of lambda. We multiply it then we take an element from the group capital G, which is a polynomial. We multiply this polynomial by the element of HP from the left, and we use, in the multiplication, we use our relation lambda to this relation, so we work modulo it. Essentially, we take the Taylor series with respect to lambda and truncate this series at the term lambda minus c to the power k minus 1. Okay, so we get an action, a left action of our group capital HP on the group capital G, and a standard definition, a function f on G is called HP left invariant if F is invariant with respect to this left action of capital HP. Okay. Now consider also another group curly H, which is a subgroup of G. We consider the right action of curly H by right multiplication on G, and a function F is called H right invariant if it is invariant with respect to this right action. Okay, now recall that these W, Q, I, J are coordinates on our elements of our matrices. Now we assume that they are functions of N and T, and we introduce the matrix polynomial, well, the matrix psi, which is a polynomial in lambda with coefficients wk, and we recall that we recall that we have a matrix Lex pair, and for a matrix Lex pair we have the auxiliary linear system. Which is this one, and we instead now we substitute in this auxiliary system we substitute the matrix psi of this form, and we work modulo that relation. Okay, and recall that small w, q, I, j are elements of the matrices capital WK, WQ. So, and if you then equations, this auxiliary linear system gives us equations, scalar equations for those matrix entries. This system of equations will be important for the next construction. It has number 12, please remember. So it is a system of scalar equations. Again, what we do here, we have M and capital U are functions of lambda, and in order to work modulo that relation, we take the Taylor series and truncate as the term of this term. Okay. Next, we consider a function Z on the group capital G. We know well the system 12.
Sergei, may I ask, can you
remind
me what you assume about matrix M of U lambda? What dependence in lambda? Is it irrational, or what kind of function of lambda you consider?
It can be anything in principle, any function, possibly elliptic, but any function, because we can use any function because we take the Taylor series, a finite.
Yes, but function, but
Taylor
come on. In your Lax pair, M of lambda defined up to multiplication by any function of lambda. So you can move up and down the poles, you know, even the value at lambda equals c. In Lax pair, M of lambda is contribute linearly, so you can multiply by any function of lambda. Why
right.
Your definition is correct.
Well, look, I have what I'm doing here is a construction which works in considered examples, right? So I take, I have a list of examples where this construction works, and the list is already quite long. So I mentioned on the first slides what kind of, for which kind of Lax pairs this construction works. If you multiply, so those Lax pairs are good. if you take a good Lex pair and multiply it by a function of lambda, it may happen that the construction after this multiplication, it may happen that the construction will not work. This I did not.
Why? It's cancel. You know, that's just cancel multiplier. You can put this multiplier in psi as a gauge transformation. Just
right. So look,
look,
my strategy is the following. I take the initial Lex pair, and first I try to simplify it as much as possible by gauge transformations. And when I have simplified my Lex pair, then I do the next step, which I am discussing here. And you suggest to go in the opposite direction. So
no, I say that your M is not well defined. You claim that everything is rigorous, and you multiply and then truncate by lambda minus c power k. I can multiply
I take
lambda by lambda minus c power k.
I take a concrete function M of u and lambda. M is given. M is given, and I do not try to multiply it by any function of lambda. M is given for me. So you know, by paper, I have a list of Lex pairs. M is given, and I apply the construction explicitly. I did not study what will happen if I try to do what you say, to multiply it by some auxiliary function of lambda. It was not needed for me to consider such a multiplication. So I take some explicit M and apply the construction and show that it works in a quite long list of examples. It is an interesting question. What will happen if you try to multiply it as you say, which I did not study. Okay, but let me continue.
Yes, please.
Because our time is limited. Right. Okay, so we have, if we take a function, an arbitrary function z on our group capital G, we know how to apply the shift operator to it because we know how to apply the shift operator to the coordinates of the group capital G, right? So the first formula defines the action of the shift operator on the coordinates. Therefore, we can apply the shift operator to any function z on G by this rule. And in general, when we apply s to the power of lambda to z, the resulting function may depend on the coordinates of the Lie group and some variables ul. And we want a condition which ensures that the resulting function does not depend on ul. And here I have theorem 2 about this. Now, suppose that we consider the function z on capital G, which is HP left invariant for some integer, positive integer p. Then the following functions do not depend on ul for any L. And this is a non-trivial property, you see. If we take an arbitrary function z, then these functions s of z, s squared of z, they may depend on ul. But if z is HP left invariant, then these functions do not depend on ul. And therefore, they can be regarded as functions on capital G. And then we need also s to the power p plus 1 applied to G, to z. And in this situation, it may depend only on coordinates of the Lie group and u. So no positive shifts of u, only u. Another statement is the following. If we have a close connected Lie subgroup H of G, and our function z is H right invariant and is HP left invariant, then these functions are H right invariant. Right, okay, and this will be used for construction of Miura-type transformations. For simplicity, in theorem 3, I consider the case capital N equal to 1, which means scalar equations. But in the paper with George Berkeley, the case of arbitrary capital N is considered. So, well, now, okay, but now let's assume that N is equal to capital N is 1. We suppose that there is a close connected Lie subgroup capital H of codimension R, and a function on G such that Z is H right invariant and is left invariant with respect to this group H R minus 1. And it also should satisfy certain non-degeneracy conditions, which are written in the paper. Well, I do not present them here in order not to overload my talk, but those non-degeneracy conditions in considered examples are always satisfied. So the main condition is that the function Z is H right invariant and is left invariant with respect to this group. And if you find in practice such a function Z, then the remaining non-degeneracy conditions are will probably be satisfied. Okay, and what happens? If we have such a function Z, it allows us to obtain a Miura-type transformation of order R. So we introduce the notation Vi is equal to s to the power I applied to Z, and we get a Miura-type transformation of this form. So this is our initial equation. This is the Miura-type transformation, and some new equation, some new difference equation will appear. So how do we do this? Here I explain the main idea. Well, so we have the assumptions of theorem 3, and then we use theorem 2. Recall what it says. If Z is H, well, by theorem, it says that those functions do not depend on UL. So by theorem 2, these functions, they do not depend on UL. So by theorem 2, these functions do not depend on UL and therefore can be regarded as functions on capital G. Moreover, they are H right invariant, and therefore they can be regarded as functions on this quotient manifold, which is important for us. And this quotient manifold is of dimension R because our group is of codimension R. Okay, now we do the following. Recall our equations. So we have the auxiliary linear system for the matrix function psi. This system can be regarded as a system of equations on the group capital G. And now we have the subgroup capital H. And since here we multiply psi by some matrix from the left, here also we multiply psi by some matrix from the left. Therefore, the whole system is invariant with respect to multiplications from the right. Therefore, the whole system can be regarded. So here, this system is on the manifold G, And since it is H right invariant, it can be regarded as a system of equations on the manifold G over H. And this is what we do. We we now consider those equations on the quotient manifold. Our functions are H right invariant, therefore they are functions on this manifold. And look, recall that in theorem 2 we had also this statement that this function may depend only on W and U, and here this was P plus 1. Now P is R minus 1, therefore P plus 1 is R. Therefore S to the power R of Z may depend only on those functions and U. And here we use this notation. Vi is S to the power I applied to Z. So therefore we get this equation. Vr is some function of the variables v0, v1, vr minus 1, and u. And we also some equation of this form. Now so the right hand side depends on v and u, and one of the non-degeneracy conditions is that the right hand side depends non-trivially on u, right? So the right hand side may depend on u, and as a non-degeneracy condition we assume that the right hand side really depends on u. Then using implicit function theorem, we can locally, from this equation, we can locally express u as a function of v0, v1 up to vr, and this will be our Miura transformation. Now, how to get the modified differential difference equation? We consider this equation, and here we have this, which is fine, and we also have ul with some indices L, but we have already expressed u as a function of vi by this formula. Therefore, we can substitute this formula here, and then we will get an evolution differential difference equation of this form. So, and this will give us a Miura-type transformation from this equation to the initial equation of order R. So I described, for simplicity, I described this construction in the case, in the scalar case, when our vector function u has only one component. But actually, as I said in the paper, the case of arbitrary number of components is considered. And also recall that the definition of the group capital G, it consists of polynomials of this form with some fixed constant c, complex constant c, and integer k. But actually, the whole construction can be done for a more general group, which is a finite product which is a product of a finite number of such groups with different constants c and different integers k. This is also written in the paper. So this is here I say that the group can be more general, a product of several groups of this form with different constants c and different integers k. Also, the capital N can be arbitrary. Okay, so this in this way I described here how to get a Miura-type transformation for a given equation. And look, when we have a Miura-type transformation for this from this equation to this equation, then this equation can be called a modified version of the initial equation. But this method can be applied in order to construct not only modified versions of equations, but also so-called doubly modified versions. What I mean here, suppose that we have three equations, E, E1, E2, a Miura-type transformation from E1 to E, and another Miura-type transformation from E2 to E1. Then E1 is a modified version of E. E2 is a modified version of E1. Therefore, it is natural to say that E2 is a doubly modified version of E. Okay, so we have modified versions and doubly modified versions. And the described method, in some examples at least, allows us to construct doubly modified versions of a given equation possessing a Lex pair as follows. First, we construct a modified version as I described. So we construct for a given equation E with a Lex pair, we construct a new equation E1 with a Miura-type transformation from E1 to E. Okay. The next step, we having such a Miura-type transformation, we can lift the Lex pair of E to the equation E1, which gives a Lex pair for E1, which is well known. So if you have a Miura-type transformation from E1 to E and a Lex pair of E, you can lift the Lex pair to E1 and get a Lex pair of for E1. Okay, but if in the matrix M for the initial Lex pair, suppose that the dependence was good on lambda and U only, but after lifting, the lifted Lex pair will depend on more than one variable. So it will depend on shifts, not only on the function, but also on shifts of it. Therefore, it is, therefore we need to simplify it by gauge transformations. So, and this, at least in some considered examples, this has been done successfully. The lifted Lex pair, it is possible to simplify the lifted Lex pair by gauge transformations as I described. And then we can apply again that construction involving Lie groups in order to construct a new equation. So we can apply it to the simplified Lex pair of E1. And as a result, we construct a new equation E2 with a Miura-type transformation from E2 to E1. So E2 will be a modified version of E1. E1 is a modified version of E. Therefore, E2 is a doubly modified version of E. Okay, so this is what is done. This is what can be done, and details can be found in the papers. Now I would like to show some examples of new equations and new Miura-type transformations obtained by this method. Well, take the well-known Itoh-Narita-Bogoyavlensky equation, which is this differential difference equation 13. Then for any constants, complex constants C1 and C2, this formula determines a Miura-type transformation from this new differential difference equation to to the Itoh-Narita-Bogoyavlensky equation. Right. The details can be, the details are in the paper with George Berkeley. And another example, consider the modified Narita-Itoh-Bogoyavlensky equation, where where bold A is an arbitrary fixed constant. So this is our initial equation now. They described here, this equation has a Lax pair with M depending on U, U1, U2. Therefore, in order to describe, in order to apply the method from the paper with George Berkeley, it is necessary first to simplify the Lax pair by the procedure, by gauge transformations, which is described in the first paper from 2000, from this year, which I mentioned in the initial slide. So in this example, it is really necessary first to simplify the Lax pair by means of gauge transformations, and details are written in that recent paper. So after simplification, we get rid of the terms U2 and U1 in the Lax matrix M, and then we apply the construction, the Lie group construction, which gives the following Miura-type transformation and the following integrable differential difference equation, which seems to be in U. That's all. Thank you for your attention.
So what is the invertible matrix M here? What kind of dependence does it have on lambda?
I can show you. Here, this is wait. I forgot lambda. Lambda must be somewhere here.
Yeah,
somewhere.
I think yeah.
Look, I have it in the paper. Let me.
Okay, yeah. Okay, I'll find it. Don't worry.
So in the paper, lambda. If there is no misprint in the paper, lambda is there. So you can. So the matrix M depends on U, U1, U2, and some dependence, some rational dependence on lambda.
Okay, thank you.
The explicit formula in the paper.
Any questions? Other questions? Sergei, could you make some hope to make a classification of such transformations?
Well, I have hopes, but it's not easy. So I'm working in this direction. In principle, we have already a quite long list of examples, but we are, I think, very far from complete classification.
Sergei, you said that, in many classifications in one class, equations are related by Miura transformations. Habibullin has a few recent classifications on differential difference equations. Can you comment on this?
Look, in the recent papers of Habibullin, a different type of differential difference equations considered. I consider differential difference equations with two variables, n and t. And Habibullin, in all of his papers, in his recent papers, he considers three variables. And it is a very interesting problem to extend the described method to the case of three variables.
Type of equations. I see.
Right. So I will definitely think about this, but have not done so yet.
Thank you.
Okay.
Hello, Ian.
Other questions? If not, I'd like to thank you once again.
Okay, thanks very much, Sergei.
Thank you.
Thank you.
Okay, we stop here.
Yeah, sure. Okay. Yeah,
Bye.
bye.
Bye-bye.
Bye.
Bye.